So my name is Krzysztof Kozlowski. If you cannot pronounce my name, I go by Krzysztof, no problems here. The talk will be about the static analysis in the Linux kernel. So I work for Linaro. I'm the co-maintainer of device tree bindings. I maintain several systems, subsystems in the Linux kernel. I actually wrote a lot of patches for the kernel, and some of them are a result of the static analysis tools. Recently, I mostly read the patches, so yeah. What I'll be talking about? I'll show the pure, real example why building your source code Linux driver is not enough, why the static analysis is useful. I will mention typical tools, Clang, LLVM, the Sparse, Smatch, Coccinelle. I will also share what you can do if you want to find work for the Linux kernel currently. And of course, every great talk should be with failure, like this, and with AI references. So let's go. Why building is not enough? So if you want to skip the talk, then too long didn't read. If you use the static analysis tools, you produce better patch, better source code. This will make the maintainers happier. And if you make the maintainers happier, then your code can get there faster. Static analysis is a way to kind of analyze how the program should operate without running the program. So the compilers usually don't do that work good, at least, because the job of compiler is to check the, let's say, the syntax and produce the binary. And the code can actually be compilable, but still doesn't work properly. Of course, the GCC and the Clang, I will mention, they already have some sort of static analysis embedded. They follow the flow. They find some non-trivial bugs, but it's not enough. So the static analysis tools, they will be at least figuring out how the program should work and whether the program is actually doing what it should be. At least that's the goal, because there is a lot of false positives there. I'll be focusing on the tools which you can use. This is open source 101, so I assume that you are not already familiar with all the greatest, let's say, open source tools here. There is something like Coverity. You can use it. It's a service. You can use it for checking Linux kernel. I will be not mentioning it because it's not straightforward to use it in your daily flow. So all the tools I'm here mentioning, I kind of focus on the practical approach, the things which you can do kind of daily during your build process, where at least I'm doing it. So why building is not enough? Let's look at this example source code. So this is some function which receives unsigned integer comment, and this comment is index. It will look at the array under this index and send this comment. So apparently there is some array of comments. It also checks whether the comment, this index, CMD, is within boundaries, I mean, within the DPFE comment max, right? And if it's too high, then return error. And the structure holding the array is defined like this. So the bottom line shows this kind of comment array with the DPFE CMD max. So this code is buggy, right? If you see the errors, then cool. If you don't see, I will say why. So look at the first comment, first line, and then the second. I will kind of extract them to show it clear, right? So first we use the CMD to dereference and look at the array. I mean, to get the element of the array, but only then we check whether this CMD is within the boundaries which we accept, which are correct or not. So we are basically accessing the array before validating whether the index is correct or not. And there are two things here. Either the code is confusing, so this is also a problem, right? We should write correct code, which is readable, not confusing code. And if you call this function with a CMD with other kind of higher index, then actually this will be true out-of-bounds access. So this will be a mistake. And this compiles perfectly fine, right? So there is the GCC or Clang, they will not report here errors. But if you use a great tool called Smatch, you will see such a nice error telling you what's happening here, so that you are testing array offset after you use this offset. So this is why we have open source static analysis tools. They will help you. They will rescue you from such bugs. But let's start easy. So let's start with the compiler. So Clang and LLVM, these are tools for, let's say, this is a different compiler, right? And most of the people use GCC. I don't know why. I also use GCC, maybe because it was working better. But it's always worth to use Clang as well to build your C code. Actually, not only C. If you ever do it, I recommend to use w = 1. This is a this will change. Let's see. This will enable additional warnings. And if you want to skip the presentation, then to log it in read, you can run it like this. I use Ccache, but it doesn't matter. You just change the CC, so the compiler, to the Clang. You can put, if you don't want to build the entire kernel, you can put the target, the makefile target, which can be a directory or subdirectory or things like that. And cross-compiling is actually very easy because you don't even need the cross-compile environment variable. You can just say that arc is ARM64. So it's even using Clang than GCC. This important aspect of using Clang, and this actually applies also to the seasoned kernel developers, that if you ever use the cleanup code, you should compile your code with Clang. So what is the cleanup code? This is something moderately new in the Linux kernel, which is like an automatic distractor. When the variable goes out of scope, it's being cleaned up. So this is something completely different for C. The syntax is kind of closer to the C++. And this is visible in the source code with the __3, or the things called guard. So both of them are being implemented with this cleanup.h. The reason why I'm mentioning here Clang, because the syntax of using these cleanups means that we don't use the standard ANSI C or Kernighan-Ritchie style. By default, in the Linux kernel, you always first declare in the function, first declare variables, then you write code. Always like this, right? If you use the cleanup.h, this syntax changes. And you both define and declare the variable the moment you use it with the initializer, which also could mean that you declare the variable in the middle of the function. And this is fine. This is the only exception in the Linux kernel where you declare the variables somewhere there, like in the middle. And if you compile with GCC, you might not spot important error here, and the Clang does, because the kernel uses another well-known feature of the early C, which is go-to, so jumping, and you should not jump over initializers. So GCC doesn't spot it, but if you use Clang, it will spot. And it's important that if you ever touch such code, so you don't have to write such guards cleanups, but if you touch such source code, you should also compile it with the Clang. Let's keep going. Next tool I want to talk is Sparse. Sparse is it's a tool typically for the Linux kernel. I mean, you probably cannot even use it outside. It was started by Linus Torvalds. Now it's maintained by Luc van Oostenrijk. Maybe I mispronounced the name, most likely. And it comes with several things useful for the Linux kernel, for the checking statically of the Linux kernel. You can run it also from the part of the build process. I don't think that there are binaries for the distros, like packages for the distros. Maybe there are, I don't know. I'm always compiling it locally and then just reference as a check argument. So as your build process, make C = 1, and then you add a check, and check is the tool. So this is the path to the sparse binary. I don't even install it, I just compile it. If you use C = 1 argument, this will check all the files which we are building. And there's also C = 2 argument, different one. And this will mean that it will run on all files on this target, even if they are already built. So in that case, I'm building it, running this check on the drivers, but you can also narrow it for the other directory. If you ever cross-compile, then remember that you also have to set the arc and cross-compile setups, or maybe coupled output, so that everything gets bigger, but the check command is the same. So I'm speaking about the Sparse, because Sparse can detect the locking issues. So it relies heavily on annotations in the source code. So the kernel sources have special annotations telling what to do with the logs. And thanks to this, Sparse can figure out that, for example, you are missing synchronization, or you are, let's say, not releasing a log, but you should release a log, which could be leading to the deadlock. In the source code, you will find several annotations that they look like this: must hold, acquires, or releases. And thanks to this, Sparse tracks the context of these logs and can tell you whether this is correct or not. And if you ever have such source code which has issue, then Sparse will tell you context imbalance, for example, wrong count at exit. And this found actually through bugs. So you can find in the source code, in the kernel, or the patches on the mailing list that there are real bugs found with the Sparse. Another typical warning or check coming from the Sparse is actually a very simple one when it tells that some symbol should be declared. This comes from the C, that basically we need the declarations, or you miss a static keyword. I will not dwell here. But I have more interesting one. And if you spot these errors, actually, it's quite trickier to fix. So there are 3 errors, and Sparse calls them as a different address space. I mean, all of them are sorts of address spaces. This is typical to the Linux kernel, where we deal with the user space, so the code running in user land, and the kernel pointers, the kernel memory space. And if you have such Sparse report, this most likely means that you have a serious security issue if you mix these 2 contexts. This means that you reference the user land memory, which is controlled by the user, in the Linux kernel context. This is a huge mistake. But there's also other case. So there's a third address space in the Linux kernel called IOMEM, or memory mapped IO, simplifying. And if you mix such case, you will see such errors a lot in existing Linux kernel. If you mix such address spaces and you see such errors, your code still probably will work fine, because your architecture it doesn't matter. You tested your code works, so it doesn't matter. But this means that your source code is not portable. It means that you cannot run the source code on, for example, different architecture which has different meanings of this memory mapped I/O. For example, for that other architecture, this memory mapped I/O requires some barriers or requires some different instructions or whatever, right? So this means that your code is not really portable. And that's quite tricky to fix later, because when you see such warnings, if you ever want to check the existing source code or some drivers, like someone else wrote them, it's very difficult to actually understand what this person meant and how this hardware works and how it should be for that hardware. So if you ever write a new Linux kernel driver, please check with the Sparse. And if you see such errors, please fix them, because later it's very tricky to fix that. Another tricky warning to fix, which you can see from Sparse, means like that, like cast restricted LE or BE16, depends, or incorrect time assignment, different base types. These are coming from comparing or mixing different endianness. So we all don't care about this, because all of the platforms now are basically little endian. However, some platforms like ARM are B-endian. And you could actually, like my damn laptop, you could try to build it with big endian, although no one does it. But still, there are some platforms which are big endian. And this means that your source code, probably your code, will still work correctly, right? But it's not portable. You are mixing the how you handle the integers between the hardware and the system. It's also quite tricky to fix it later. So if you see such warnings, better to fix it early. If you want to tease your brain with how such source code, how such issue could look like and how it could be fixed, and the explanation why, then here is a nice reference learning experience. Sparse is not really a true static analyzer. The true static analyzer is Smatch. So this is the core thing I would like to talk here. This is a great tool developed by my colleague, by Dan Carpenter. It can be used for the user land code, but I think we all kind of focus here on the kernel. I think there are also no packages like in distros for it, so I'm also building it in some directory and referencing the path in the check tool, the same as I'm using Sparse. So, and the Smatch has some kind of kernel checker script which you can use to help you, but you can use it as a part of your check for the make build process. If you use it, then remember about the -p = kernel to enable kernel-specific checks for the Smatch. So Smatch is really static analysis in a way that it tries to guess the intention between the source code. So it tries to figure out what you wanted to do and then check whether you are doing it. And even if there is no real bug, it actually tells you that the code could be more readable. And this is a nice feature of the Smatch. It can check whether you are properly releasing the resources. So for example, not only the memory resources, like a memory allocation, but also the clocks and I/O mappings, whether you are releasing them. It can figure out whether your variables are not initialized, especially in the context of, let's say, if-then branching. can figure out possible null pointer references, and also points out confusing indentation, which means that some source code is indented like it should be doing something else. And this actually also can lead to incorrect code. And Smatch, to do this, has some kind of assumptions. And this, again, this is a real part of the source code from the kernel. This is part of the probe function, and we get some sort of get match data. We assign it to the ddata variable, to the pointer, and we check whether the pointer is not null. If it's not null, we do something. It's not an error, can be null, right? But if we do something only if it's not null. Later, this function was doing something else, was dereferencing the data and checking whether the quirks contain this specific quirk. And if it has this quirk, yeah, do something, handle it, right? So the code is also not really correct or confusing. Why? Because first we check if the data can be null. So here we assume that it can be null. But here we dereference it unconditionally. So either it is null, or either it is possible or not. I mean, it cannot be both cases, right? And if you test your code with the Smatch, it will tell you that such nice warning that we previously assumed that the data could be null. And this means that your code either is buggy or confusing. Of course, this means that Smatch can get it wrong. So of course, there can be multiple false positives, especially on the clever code. It can fail. Hopefully, people write clever code intentionally, not by mistake. However, if you develop Linux kernel drivers, you should probably not write clever code. You should write readable code. At least we try to write readable and maintainable code. And Smatch really points real issues. Here's another example of how such confusing code could look like, and Smatch really points that it's something to improve. If you ever want to fix the Smatch warnings, remember that it can be a false positive, so remember to focus on finding the root cause of the warning, not just making the warning disappear. Another tool I would like to talk is Coccinelle. So this is, again, not really a static analytic tool. It's rather a tool for pattern matching and text transformation, or creating semantic patches. It was, I think, created by multiple people. However, the most known person is Julia Lawal. She's presenting on many conferences about the Coccinelle. We use it a lot in the Linux kernel, actually, to perform kind of big transformations of the source code. So whenever you need to change a lot in multiple places. It's like a common task for refactoring or mass code transformations or spotting common errors. Coccinelle works on semantic patches, so these transformations of the source code, and the kernel sources under scripts Coccinelle already have such several of transformations, such patches, which you can use. Right? You can also write new ones. Coccinelle comes from a distro. Probably you can also compile it, but this actually is a distro package. So if you want to run Coccinelle, there are two ways how to do it. First of all, there are two modes how to do it. One is report mode. So this is the one where the Coccinelle will tell you what's wrong. And this is the Cocci check. But if you add argument mod equals patch, then it will actually change the source code. So this is this kind of transformation part of Coccinelle, in a way that you can write a semantic patch, and the semantic patch will create more patches, will change the source code. We actually use it to do the actual work. Not all of semantic patches are this mode of patching. Most of them are, they must support the reporting mode. The output of the Coccinelle can be unmanageable. Then you can add debug file, Cocci, or debug file, whatever, to move the debug stuff outside, and then focus only on the warnings coming from the Coccinelle. And if you ever want to check specific files, there's different syntax. I leave it for reference. You don't have to learn it, but you can also run this Coccinelle as a check tool. In that case, you reference the scripts Cocci check, and this also means that if you have built output variable in a way that you have a build directory somewhere deeper or different place, you might need to tweak the paths to the script Coccinelle. And great thing of the Coccinelle is that you can actually write your semantic patch, and you can run only one specific patch. So then you add it as a Cocci equals, and you point the path to the semantic patch. You can take it from the existing sources of the Linux kernel or write a new one if you ever do it. Now, why I'm speaking about the Coccinelle? Because I review a lot of patches, and I see quite a lot of 10 years old code. And 10 10 years ago was kernel 4.0. I mean, time flies, right? So unfortunately, that when people upstream Linux kernel drivers, let's say they upstream something from vendor tree or whatever the manager asked them, or they found somewhere driver and they do it for fun, they send what they see. So they also post to the mailing list 4.0 kernel stuff, kernel code. And how do we recognize them? Well, yeah, I mean, during the 10 years, kernel changed, right? So this old source code which you posted is probably missing some things. It might be following old patterns, like not using the def error probe to handle the thread probe. Maybe it doesn't use the def interfaces, so these are the resource managed interfaces. Most of the new drivers are converted to this. Maybe it prints too many errors, because before every driver was printing errors, and we moved these messages to the Linux kernel core. Maybe it forgot to off-node put, so to release the reference to the device tree node, because in the past we didn't care about this, right? 10 years ago. Or maybe just mixing compilation between when you open firmware, device tree is disabled or ACPI is disabled, or many other trivialities, like an old coding style which we changed during the 10 years, and poor coding style hides the real issues. And for me, my favorite litmus test, like a 99% to figure out whether this is a 12-year-old old code which we are sending to mailing list, is this one. Now, this is actually a real patch. And the problem is this one. So the owner, this module. This is gone since 12 years ago. So what's wrong here? The author did not run Coccinelle. Or actually, the other problem is that the author took 12-year-old code and tried to send it. And maybe you should just take the newest kernel driver and build on top of the newest kernel driver, maybe different process. In any case, run Coccinelle. And independently of the Coccinelle, there is here this off-match pointer, and this is disliked, and it might lead to some warnings of if you disable the OF, but doesn't matter. So we really use Coccinelle to transform the kernel, which means like old style goes to new style, and also means that we don't want to see this old style. So if you ever write a new Linux kernel driver, we don't want to see if you write it in an old way, please. And this will help a lot, because you should not use reviewers to do the automation stuff, do the tools to do the automation. Leave the reviewers for the, let's say, non-trivial things. So, but should we use these tools to find existing source code? Now I'm focusing kind of here on writing new Linux kernel drivers. However, shall you check the existing sources of the kernel with all these tools? Right? Well, yes, go ahead. I did it. I made a lot of patches with it. So use any of these, Coccinelle, Smatch, Sparse, Clang, if you want to have your first contribution to the Linux kernel. Actually, easy way to start your work. Of course, the only disclaimer, caveat here, is that many low-hanging fruits are already picked up. So many trivial things to fix up are already done. Therefore, this was maybe quite good advice to do it, I don't know, 5 years ago. Maybe now it's already too late. And few other disclaimers. So if you ever do this, if you ever run all these tools on the Linux kernel, existing source code, then please always fix the cause. Don't make the warning disappear. I mean, we are not interested in making the warning disappear. We are interested in finding the root cause. And this is actually quite tricky, right? Consider that it might be false positive, especially in the case of the Smatch. Think how you can test your code, if it's at least possible. And if you use some tool, then please always mention that tool in the commit message and trim the warning and include the pieces of this warning in the commit message. This is very, very, very useful. If you want to use Coccinelle, then just remember that not all of the semantic patches from the Linux kernel, the transformations, are welcomed by every maintainer. Especially there is one transformation there which does really trivial, not important change. And some maintainers might like it, some maintainers might not like it. If you check the mailing list, there's a company vivo.com which does it a lot. So maybe don't do this because you will clash with them. So, but the Coccinelle scripts which are related to actual issues, these are welcomed. So of course, we need to speak about AI. So using AI when writing new code, like whatever you use in your workflow or even send it, yeah, it's up to you, right? But please don't send patches or don't send more important bug reports based on the large language model tools. Why? Because these are not static analyzers, and you can really convince them to tell you anything. And we saw many of such reports that people didn't understand the code, and they sent whatever bug report that there's a bug here because the ChatGPT told them. This is not a static analysis, right? It's language analysis. By the way, it's language analysis, so it means also it might be useful for actual code review. Because code review, we don't look at the entire source code, we look at the pieces of the source code, so from that point of view. But static analysis is a bit different. Of course, disclaimer, if you are an experienced kernel developer, then maybe you can do it because you will filter what this LLM is telling you, right? But if you're not an experienced kernel developer, how can you know that the tool is not lying? How can you know that it's not hallucination? So just be careful. And why I'm speaking about this, because this will grow in context. People will be using these tools, and this will lead to wasting maintainer's time, wasting of the reviewer's time. We'll have to deal with the incorrect or really fake findings because the ChatGPT told you that. And even more important, if the person does not really understand the code, right? And I'm, as a reviewer, saying, listen, why you do this? It feels wrong, right? And this person will ask my question to the ChatGPT and then send ChatGPT answer to me. I will be talking with ChatGPT. I don't have any interest in talking with ChatGPT. Please don't make me. But of course, if you as a person can answer to me, then yeah, it's fine. But I'm afraid that yeah, I will be talking with AI. So this is also a straightforward way to get unfortunately ignored. Why? Because wasting my signer time. If we ever do this, right? You can always don't listen to me. But if you ever do this, please mention this in the commit message. And some more details might emerge during the maintainer summit, December. It's planned for the plumbers, both from the point of view of annotating the kernel patches, of any patches with AI, so generate something with AI or whatever. This one thing, but other thing, whether we even want such patches. What's the possible legal risk? And what is your data set? What is the tool? Maybe the tool is patented, so maybe you cannot even use it to submit open source code, right? Who knows? Anyway, more details will be in December, hopefully. And with this AI, I think I'm getting into the talk. So maybe there are any questions? No questions so far. I don't see it. Yeah, there's a hand there. So the question was, to repeat for the recording, whether I have specific workflow, which tool I use. Yes, I'm always first building with the Clang, because it's the fastest, the easiest. I have already used my scripts, alias for the bash, and then usually Smatch. And then for the last is Sparse and Coccinelle. Coccinelle I usually don't run daily, but from time to time I run it. So Smatch and the Clang. So the question was not a question. First was a comment that I didn't mention check patch. And second was that maintainers should incorporate these tools in the workflows so that they will be already maintained. So yeah, obviously, right? I didn't mention check patch because it's a standard Linux kernel tool. If you ever want to create a Linux kernel patch, every guideline will tell you run check patch. So I assume that, but maybe I should mention it. This is not a static analysis tool. It's the collection of basic sanity checks on the check patch. So before you send a Linux kernel patch, run this check patch tool. About the GitHub, yeah, I agree. I mean, that's the big problem of the kernel community, that we don't have uniformed way of automation of this easy checks by the tools, right? So there is the Intel's bot, so the LKP, Linux Kernel Performance Test Bot. He actually runs these tools. So this is a huge collection of virtual machines or real machines, and they run on the maintainer trees, on GitHub trees, and on many patches on the mailing list. And they run Smatch, Sparse, and they run I think Coccinelle as well, and they run the Clang builds. So, but you should not rely on this. You should always do it, and the best if you incorporate it in the in your workflow. And the maintainers, yeah, you know. I mean, yeah. So, question. So the comment was that the TI has a tool, kernel checker, which already incorporates multiple of these other tools which I mentioned, and you can use them like integrated flow. So I'm not aware of community-wide solutions. I indeed remember that TI has a tool. I think Nishant was using it, I mean, for himself, right? And it didn't. I don't think it kind of grew outside of TI, especially because now I recently learned that Qualcomm has its own tool. They also publish it. It's called Patchwise. So now we have two tools, and we can make a third tool to substitute these two tools, and we have three tools. My favorite AI checker? Yeah, that's. I can only tell you after the few beers. Question far away?
How expensive are these checks in context of like performance or,
Good.
how often do you run them generally, like after each change or?
Great question, yeah. So the question was, how expensive are these tools in terms of performance of your build process involvement? So all of them, the Clang is like just compiling very fast, Sparse also the same, Smatch very fast. So they are very, very, very fast, no problem. If you can build it, you could actually make a command for building with all of them, and this will just probably double the speed of building. So the same as GCC takes, then they will take. Coccinelle takes much more time. So this is why I gave there several comments which you can narrow the Coccinelle per specific semantic patch or per let's say directory. But Coccinelle takes significantly more time, up to, let's say, if you check entire kernel, probably, I don't know, a few hours. And if there are no more questions, I'll be also having, there is one more question, yeah? Great question. So if Sparse can detect deadlocks by looking whether the logs are acquired the same order and release the same order between the two places. Actually, I don't know. But this would be, I mean, this is doable, right? If you can track the context of the logs, then you can also track whether they acquire the same order, right? But I don't know. Anything more? No? Then I will have a speaker office hours on Wednesday, and if you have more questions, just drop by and yeah, ask them. And if you want to ask about this damn laptop, please, if you know how to fix it, then yeah. All right, thank you very much.